Hello, everyone. Welcome again to our discussion of critical reasoning. Today, we're going to start exploring Chapter 11 in the Vaughan textbook, which deals with judging scientific theories. All right, so that's going to be our focus today for this video. So let's begin by making clear what sort of questions we are actually interested in when we're thinking about scientific inquiry in general. So, when we're considering scientific inquiry and the scientific method more generally, we shouldn't be focused on questions like, do we actually really know whether the Earth rotates around the sun once a year? Or questions like, how exactly does a quantum computer work? Or maybe more general to your own life, am I going to pass my biology class or physics class? No, rather, when we're doing scientific studies, when we're thinking about the scientific method, what we're actually aiming at is some form of understanding, some way of thinking about how is it that science is actually done. Uh, we need to think about how to evaluate the knowledge that scientific inquiry yields. And whether or not we actually understand and can make sense of the world around us, making sense of and having an understanding of the way the world works, of what's going on around us. This is really kind of the aim for our purposes, the aim for scientific studies, inquiry, and the scientific method. We live at a time when there's just a rapid amount of advancements and human understanding for all sorts of different reasons. One way that I like to think about this is that we currently live in a sort of Goldilocks period here on the earth, where we are alive at a time where it's just right for scientific understanding to explode, for human knowledge to really take off. So what do I mean by that? Well, we live at a time where communication is advancing in many different ways. We got advancements like the written press, the internet, the ability to, with the push of a finger, be able to speak with somebody on the other side of the world. We're able to send satellites into space and to travel to other distant planets and to explore the surface of Mars. We're able to do all sorts of really amazing things at a time when we would not have been able to do that even 50 years ago or 100 years ago, certainly not 1,000 years ago. And if you think about the way the cosmos works, the light that travels from the distant stars takes many light years even to reach us. And so the light that we're seeing in the night sky tonight, took, millions of light years just to get to the surface of the Earth. So we live in this weird sort of Goldilocks point in our existence here on the Earth, where we're alive at just the right time to be able to make huge advancements in our understanding of the universe. A lot of these factors, as it relates to scientific studies, actually grew out of the Cold War. It was really largely the Cold War that put a lot of money, a lot of attention into scientific development. Essentially, what happened was coming out of World War II, with the advancements in technology that led to the atomic bomb and to splitting the atom, and the things that we were able to learn and grasp from those moments. Those advancements gave rise to a kind of arms race between the US and to the former Soviet Union, as well as other countries throughout the world, where there was a race to achieve the best technology, to put a man on the moon or a human on the moon, to be able to do as much as we could to expand our understanding of the way the universe worked. So lots and lots of money was put into to industry, to academics, in order to discover new technologies, new ways of communicating, new weaponry, for instance. So all of these things really grew out of the Cold War. So it influenced the way we understand science and the way science is done. And certainly it influenced what academics looks like. So we should really be careful when we're thinking about the scientific method because while it's a method that's been developing for hundreds of years, because really it's the Cold War that gives rise to science as we recognize it today. Now, I also want to remind you of things like the replication crisis. We talked about this a few weeks back, where the replication crisis is an indicator that we still need to make progress. There's still things that we need to work on. If you recall from when we talked about this previously, the replication crisis is the idea that there's research that's being done without being reproduced in other places or by other research teams. And if we're failing to reproduce the findings that we get from different scientific studies, well, then that's not really quite matching or meeting all of our expectations of what the scientific method ought to be. And so you should think about that as it relates to the development of science, because we want to be able to have the best results, which means that we need to be able to reproduce those results. Likewise, we should be concerned with factors in our own contemporary society that leads to a rejection of scientific knowledge. And I think a lot of this has to do with several things. On the one hand, we've got the spread of social media and the spread of misinformation, and that really does quite a bit to why I think people are rejecting quite a bit of scientific knowledge these days. And we'll talk about that in more detail in the coming weeks. But on the other hand, I think it's because a lot of people just fail to really quite understand what science is, what the process is, what it involves, and recognizing that it's a matter of trying to understand the world around us, not really a matter of trying to prove some particular theory or to justify someone's ideology. And that suggests that we'll need to pay close attention to things like the different legal and ethical challenges that certainly will accompany the future next steps in the advancement of scientific understanding. I think this is something that we're seeing clearly in the development of artificial intelligence and large language models, insofar as there's certainly legal and ethical issues that are built into or baked in the cake with regard to this kind of technology. So for this module, I'm also going to include some other videos for you to watch, where we think about how science has developed in more detail, these different scientific revolutions, as we might call them, specifically as it relates to Kuhn's approach to scientific development and our understanding of the scientific method. So pay attention to those videos. But in this video, we're just introducing some of the topics that we get in this particular chapter, right? So one of the things that I want to do is think about how these issues might be new, but they also have been around for many years. So let's then turn to the question of what exactly science is. How should we define this term? What are we talking about when we're talking about science? Generally speaking, I think that there's no clear-cut, unproblematic, or universally accepted definition of what science is. But I do think that we can offer some fairly clear way of understanding it. Kind of ostensive definition where we point to certain things and we say, these are the things that we're talking about here. So, in general, I think that we can think of science as a very careful and systematic search for knowledge and understanding of reality. Not necessarily some ultimate truth, but a kind of understanding of reality through the formation, testing, and evaluation of different theories. Or maybe a better way to put that is through the exploration, testing, and evaluation of explanations, which is why inference to the best explanation, which was the topic we dealt with in the previous module, why that's going to be so important to our understanding of the scientific method. Because really what we're doing is we're dealing with scientific explanations. When we're thinking about theories, that's what we're thinking about. We're not thinking about some ultimate grand theory that tries to give us some ultimate truth. We're looking at explanations for a phenomenon. We're trying to understand what is going to be the best explanation for the things that we observe. So here's the way that Vaughan puts our understanding of science in the textbook for chapter 11. Speaking of what science is, Vaughan says, quote, "It's the most powerful tool we have for uncovering truths about the world and distinguishing between what is real and what is not. It has been successful in helping us acquire knowledge because it methodologically guards against common biases and prejudices of the human mind. It resists partisan pressures and popular opinion, accepts nothing on faith, and demands hard evidence and solid reasoning. Right, so that's going to be our very general account of what we're talking about when we're talking about science here. It's a kind of a tool that we use to uncover truths, not some ultimate truth, but an understanding of the world around us through this methodological process that guards against different errors, guards against prejudices and biases and so forth. So I do want to be careful though, because there are different things that I sort of disagree with Vaughn about. I keep mentioning that science is not an uncovering of the truth of the world. I think that that's a bit problematic, and I'm going to explain why here in a second. I think putting it in those terms as uncovering some sort of deep fundamental truth is a little misleading. It's a little problematic. So to cash out why I think that's the case, why I think we need to be careful here, let's give some examples, some things that I think Vaughn would likely agree with. Right, so we've got different so-called quasi theories out there, like string theory, for instance. String theory, or some other version of a theory of everything, where this theory of everything is going to bring together all of our other theories in some sort of unified theory that tells the story of the world and all of its most fundamental aspects. And I think that people have been trying to say something along these lines for 20, 30, or more years. It seems like the theory of everything is always just right around the corner, but it hasn't ever happened. And I think that there's a reason why it hasn't ever happened. The reason why string theory is no theory at all, the reason why we're never going to have a theory of everything in this regard, is because it's not testable. It's not the sort of thing that could ever be wrong. It's at best it's mathematically equivalent to lots of other different explanations, but it's not testable. We can't actually perform any experiments that would allow us to confirm any results. So it has no predictive power, right? Physicists have been trying to find a way to show that string theory is testable, that it does have predictive power for a very long time, and it looks like that promise has not ever come to fruition for a very good reason. Because science is not in the business of telling us what the truth is for everything. Rather, science is focused, right? We've got certain goals. Take, for instance, the Cold War and the different scientific advancements that came out of the Cold War. Lots and lots of money was put into different research projects for a specific purpose. It either came from the government or maybe from private industry, but the general idea here was that they had some goal. This wasn't an ideological issue per se. The science itself was not an ideological issue. Yet at the same point, somebody had to fund this research, either the government or someone else. And so there was some sort of background information, background understanding, or background knowledge, we might say, that we're sort of tipping the scales in one way or the other. And that's because uh, we're not interested in some sort of absolute truth when we're doing science. Rather, we're interested in something more like what's true enough in order to get the job done. What's true enough in order to uncover what it is that we're interested in, or with regard to whatever goals that we happen to have. Right. So this notion of true enough, I think, is really, really important. Various philosophers, for instance, Catherine Elgin has this book called True Enough, where she cashes out some of these points. But what these philosophers are trying to show is that when we actually go and look at what scientists are doing, when we actually observe and pay attention to how science works, how it operates, it looks like we're not searching for some ultimate absolute truth. Rather, we're dealing with this notion of what's good enough, what's true enough. Take, for instance, the example of a curve smoothing. This is where we have a graph with a lot of different points on the graph. Those points are all data points. And then we smooth out that curve, right? So that way we can see, what direction the graph is pointing in. But that smoothing of the curve itself is only sort of a true enough indication. If we were to stick with only what the data points say, then we would not be smoothing out the curve. It would be a jagged sort of curve. And so that's an example where we rely upon, these results in a way that is kind of hinting at this notion of true enough rather than some absolute truth. We also have various laws and the laws of physics that are called ceteris paribus laws. These are sort of laws that tell us, all things being equal, this law of gravity works. But notice that in the real world, things are not equal, right? So the law of gravity works when we ignore a bunch of other information. But nonetheless, it works. That's what we're interested in, right? The law of gravity explains why bodies move the way they do through space and so forth. But if we were to actually focus on what's absolutely true, some deeper fundamental truth, then we could not use a ceteris paribus law. We would have to include as whatever other information, background information is needed, because we wouldn't be able to just say all things being equal, because that's the way the world is. The world is not all things being equal. And that seems absurd. That there's no reason why we should do that, given the fact that these laws work. They work really well, in fact. And so that seems to suggest that in science, we incorporate these ceteris paribus laws because they work, not because they're absolutely true or getting at some fundamental truth, right? There's lots of these sorts of idealizations that occur in sciences. Idealizations are where we are imagining some hypothetical situation. A great example of this are the ideal gas laws. The ideal gas laws are not describing some fundamental truth. Nonetheless, we would not have rocket science without these ideal gas laws. We would not be able to send people to the moon without these ideal gas laws. So again, they work. And that's what seems to matter. They're true enough, even though they're idealized, right? And it's interesting because idealized laws, like the gas laws, are technically speaking false, but they are required for our ability to send somebody to the moon or to send a satellite to Mars or to Jupiter or something, right? So without them, then we wouldn't be able to do these things. But nonetheless, we know that they are technically false. Yet we're including these known falsehoods into our best theories. Again, we got something very similar going on with regard to stylized facts. Take, for instance, economics. Economics deals with concepts like the average family or the average household, right? Well, these are stylized facts because there is no average family, there is no average household. Nonetheless, our best economic theories operate and work because of these known falsehoods that we incorporate into these scientific theories. And so that looks problematic if we think of science as being some sort of search for an absolute fundamental truth. That's just not what science does. Science operates on this notion of true enough rather than some fundamental truth. Indeed, I would submit that Vaughan would actually agree with this. And that's because the reason why science is such a powerful tool is simply because it's highly successful, right? We are able to use these ceteris paribus laws or these idealizations like gas laws. We're able to use these in a reliable way, right? The method is in some sense self-correcting. We're able to correct for various errors. And these features of science make possible a deeper understanding of reality, even though it does not uncover some ultimate truth about the world, right? And that's because science is not dogmatic. Science always allows for the possibility that it could be changed if we have better evidence, if we have a better understanding or a new theory or a better explanation, right? We're always going to allow for the possibility that we have something wrong, that we need to update our theories or our views in some regard. It's not dogmatic. It can change. It has changed, and it will change in the future. And that then suggests that science is not ideological, right? Science is not a worldview. Sometimes people get this wrong. They think of themselves as, well, I subscribe to a scientific worldview. But there is no dogmatic worldview that all scientists ascribe to, right? Science is a way of figuring out how the world works. And there are a wide range of different scientists with all sorts of different worldviews, right? Some scientists are Christian, some are Muslim, some are Hindu, some are atheists. They're just because somebody ascribes to a scientific process does not mean anything about the rest of their views, right? Maybe they're Republican, maybe they're Democrat, maybe they're independent. Who cares? That part doesn't matter. It's when science is being used for ideological purposes that's problematic. Science is not in the business of saying, well, this is the correct worldview, or if you believe something falsely or wrongly if you have the wrong worldview that's inconsistent with science in some regard, right? Science is a process of inquiry. It's not some sort of philosophical position, right? Science is not motivated reasoning. Remember from previous modules where motivated reasoning is this idea where someone uses reason and evidence to support a position that they already hold. And that would be like a conclusion in search of some evidence, right? Science doesn't work that way. Science actually eliminates bad views, or science eliminates bad explanations until we're left with the best explanation. We're not searching for evidence that's going to support what we already pre-theoretically accept. Rather, we are looking at the possible explanations that exist in logical space. We're evaluating those explanations based upon the different scientific virtues that we have at our disposal, and then we are eliminating the bad explanations that don't stand up to the evaluation. Likewise, we need to be careful to make sure that we're not confusing science with technology. Science is not the same thing as technology. There's many different technologies that are born from all sorts of different scientific inquiries, and many of these things have made a huge difference in our everyday lives. But science itself is not the same thing as that technology. It's distinct from technology itself. So think about these sorts of examples. Communication and propaganda. Emerging technologies that focused on communication that led up to World War II, things like the radio and television, these new emerging technologies at that time were used for the purpose of propaganda by the Nazis. And of course, the United States did this as well. We're not innocent in that regard. And they still are. Communication is still being used for propaganda reasons. This is certainly happening in social media and online today. Right. So, in that regard, then, this emerging technology of different forms of communication itself is distinct from scientific investigations, especially when it can be used for the purpose of propaganda. Another example is Galileo and the telescope, right? Galileo was able to make advancements in our understanding of the Earth's place in the solar system because he was able to create these new lenses. Right, so he grinded the glass and was able to create a telescope, and this allowed Galileo to actually look at the moons of Jupiter for the very first time, and he was able to see that the moons actually go around Jupiter, and that gave us a reason to believe that the Earth was not at the center of the universe. Another great example is Alan Turing, one of my own personal heroes, and Alan Turing's advancement of what we now recognize as a computer. Right, Turing used this concept of a computer or a Turing machine in order to break the Enigma code. He actually created this machine, which allowed us to break the Enigma code, which made a huge difference in the Allies' success over the Nazis during World War II. Likewise, Einstein and nuclear energy. Nuclear energy emerges out of our scientific understanding of atoms and how to break the atom and so forth. But the technology itself is distinct from the science. Many things actually emerge out of World War II, certainly things like space exploration. Again, this is a huge and important part of the Cold War, sort of this race between the US and the former Soviet Union in order to put a person in space and then put a person on the moon. But another really interesting example comes from World War II is ammonium nitrate. Right after World War II, we had a huge amount of surplus ammonium nitrate, which was used for explosives during the war. And so the United States decided to repurpose this ammonium nitrate for contemporary commercial farm use. Right, we use this to create fertilizers that allowed us to produce much more food on a smaller area of land. And so this then gave rise to the modern supermarket. So when you go to the grocery store and you buy your food, and the contemporary modern food industry, all of this comes out of World War II, and the fact that we were putting to use ammonium nitrate for fertilizers in order to produce more food in a smaller area of land. So clearly, there is this intermixing and mingling of technology and science, but they are not the same thing. They are distinct. So now let's move on to talk about what the scientific method is more specifically. I think there's a kind of popular notion of the scientific method as being this, this crazy haired man in his basement mixing chemicals or something along those lines. That view of a scientist, I think, is kind of like in the common zeitgeist, but it's false. That's not what science is at all. I think there's also this kind of characterization that we get from our early education experience with being taught what the scientific method is, these different steps and so forth. But I think that that's also a bit of a misrepresentation of what the method actually involves. So, first of all, let's recognize that science is fundamentally collaborative, right? It's an interdisciplinary and a social enterprise. You never have a single person, at least not in contemporary science, you don't have some single person that's doing all of the work. Rather, you have a group of people, a team of people that have different responsibilities, working in an interdisciplinary and social fashion in order to pursue whatever goal it is that that particular study is focusing on. Right. So science consists of research programs, and these programs include many different people, many different scientists. And each of these people have various roles or different jobs on the research team. So, for instance, I am a part of, for the past few years, I've been part of a $2 million research grant through the National Science Foundation. And my role is to create embedded ethics modules focusing on the ethics of artificial intelligence that then gets used or implemented in different STEM courses, and the graduate students in those fields will go through and participate in these embedded ethics modules focusing on AI. Right, that was my role in that particular grant. Of course, my role is very different from most of the people on this particular grant, on this research program. But I think that this is a good example to show how the program itself is interdisciplinary, it's social, and it's collaborative. It has many different people working on the team. Right. So the notion of the scientific method as it's taught in school, where it consists of these 5 different steps, is, I think, to some extent, arguably an oversimplification of what scientists are actually doing. At best, I think you could say that these 5 steps are practiced in the hard sciences, where what we mean by the hard sciences are like physics and chemistry, maybe biology, and the soft sciences. It's not clear that the 5 steps are followed, at least not to the same extent. Where the soft sciences are things like social sciences or history or economics and so forth. So really, it's in the hard sciences where we see these 5 steps being employed in the scientific method. But all branches of scientific inquiry, both the hard sciences and the soft sciences, do share many of these features in common, which we can represent using the 5 steps. So here are the 5 steps. We first begin by identifying some problem, or we make clear what the purpose is, right? We have a research question that we're going to investigate. And the real world, this is actually done in lots of different ways. For instance, somebody might do some sort of a literature review, or they might do some data mining. Maybe somebody notices an important anomaly. And so, in that real world situation, maybe there's some unknown disease, and then they pose a research question, and that's what they're going to attempt to answer. Secondly, they devise some sort of a hypothesis in order to try to explain the relevant phenomenon or whatever it is that they're observing. And notice that this hypothesis is actually giving us some sort of an explanation for the thing that's observed, for the phenomenon that we're interested in. And science is in the process of ruling out bad hypotheses or bad explanations. That's this process of falsifying other positions. And that's what we do in this process of testing and evaluating explanations. Now, the third point, the third step is to devise a test, or devise some way to test the implications or to make predictions. And there's lots of different ways that this can occur. Oftentimes, this happens using quantitative data, where we collect data, we evaluate data, but we can also use qualitative data where we introduce questions or surveys. Most students, I would say, are at least somewhat familiar with either experiments run in a lab or maybe some sort of empirical observations that are done in a field. But I think very few students, especially the public and more generally speaking, are familiar with what's called scientific modeling. Scientific modeling is extremely important in contemporary sciences, right? We use this sort of modeling process to try to get an understanding of which explanation is going to be the best explanation. We run our predictions through a bunch of different models and see what the results are. And so that's this process of performing the test, right? Scientific modeling arguably is the primary way in which we do scientific testing nowadays. We run the data through a model and we test it that way. And then finally, the fifth step here is that we either accept or we reject the hypothesis, which involves this process of publication. And importantly, we should repeat the whole process. Right, this is the idea of replication. And if we're not able to reproduce the findings, the results over and over again by different teams, different processes at different times and different places, well, then that shows that there's some problem. And so we need to go through this process of repeating what's been done. So now there's this question of judging different theories. So this is actually a really important part of understanding how to evaluate scientific explanations. We have what's oftentimes referred to as scientific virtues. These are the virtues that we use to judge scientific theories. Right? So on the one hand, we have consistency. We want our explanations, our scientific theories, to be consistent with data. We don't want it to be inconsistent with outside information, and we certainly don't want it to be internally inconsistent. So if it's inconsistent in some sense, then that's a reason to reject the explanation or the theory. We also want the explanation to be something that we can test. We want it to be falsifiable, right? So if there's no possible way to show that the explanation is false or that the theory is false, then that should be a non-starter. All right. We want to be able to test and to falsify any theory, any explanation. So if it's not even possible to do that, then we should reject it. Right. That should be a dead giveaway that we're not dealing with a good explanation, a good theory. We also want it to be fruitful. A good theory or a good explanation would tell us about an array of different things. So not only would it help us explain some particular thing that we're interested in, but we can make connections with other things that we're interested in, right? So it should have a high amount of fruitfulness in that regard. Its scope should be large enough to be able to be fruitful in those regards. Its scope should tell us about numerous different things if the explanation is a good explanation. We also want a scientific theory that's simple. This is the idea of Occam's razor. We don't want more information or more complexity than what was needed in order to make the explanation work, right? So the simpler theory oftentimes is recognized as being the better theory. But we need to be careful here. When we're thinking about simplicity, we need to balance that with other things. Imagine that we've got one theory and it's very, very simple. But that particular theory or that explanation does a really terrible job of explaining things, or maybe there's no good way to test that theory. Well, just because it's simple doesn't necessarily mean that it's the best theory. If, for instance, I have one theory that's very, very simple, but it can't be tested, can't be falsified, so it doesn't give me any results in that regard. And then I have another theory, and it's not necessarily as simple, but let's say that it does a very good job of making sense of the data. It can be tested, it is falsifiable. Well, then between these two theories, I should go with the second one rather than the first, even though the second one is not as simple. Nonetheless, let's suppose that I had two different explanations for some phenomenon. Both of them are empirically equivalent, right? So they both do the same job with regard to making sense of the data. They're both equally testable, equally falsifiable. But one is more simple than the other one, then we would go with the simpler theory. Finally, we've got this notion of conservativeness. This scientific theory tells us that we should look for a theory that does a good job of making sense of our background knowledge. Or another way of putting that is that it does a good job of fitting in with what we already know. It does a good job of making sense of our intuitions or pre-theoretical ways of approaching things, right? We don't want a scientific theory that's going to completely change the way we observe everything, the way we think about and understand everything, unless if it's required. So take for instance this idea of black holes. There was a point in time when this notion of a black hole was actually used as a reductio ad absurdum against Einstein's theory of relativity. Right? The idea was, well, if Einstein's theory of relativity entails that black holes exist, and black holes are just radical, weird things, it would completely revolutionize the way we think about and understand the universe. Well, then that would be a reductio, right? That would be an absurd situation. It would violate this principle of conservatism because we would have to change so much. That would then suggest that we should reject Einstein's theory. But it turns out that actually black holes exist. And so we have really good reason to think that black holes exist. That means that actually some aspects, many aspects of the way we understand the world do need to be radically changed. Right. So conservatism tells us basically we want an explanation that fits what we already know, unless there are very good reasons to change what we already know. Like in a situation where we have a scientific explanation or theory that just does a really fantastic job of making sense of the data. Or it does a great job of meeting all the other scientific virtues that we use when we're judging a theory. Well, in that sense, then conservatism might be less important than some of the other virtues. So this is a kind of a balancing act where which scientific virtues we are going to rely upon might change depending upon what our goals are, what it is that we're interested in trying to do in the first place. All right, so that is a really quick romp through some of the information here in the chapter 11 of the Von text. Again, I've got some other videos that I want you to watch that go into more detail about our understanding and judging of different scientific theories and the scientific method. So that's what I want you to do for the rest of this module.